vector E2. The nth column will be the vector En. I place one after another as columns. So clearly I get an n by n matrix, right? So now it's possible to prove that the reciprocal basis set, suppose I take the inverse of the matrix E and then take its transpose. These operations are sort of exchangeable. You can take the transpose and take the inverse, or take the inverse and take the transpose. Taking the transpose is very important. You get another n by n matrix, and it's possible to show that the columns of this matrix, E inverse and the transpose, are given by the reciprocal basis vectors. Now this procedure is valid even for an n-dimensional case. However, there is another method that will work here for this three-dimensional case, and that is particular to this A1, A2, A3, and B1, B2, and B3. So first thing what I would know is A1, let us take, suppose let's say we are given A1, A2, A3. We are given this vector. Now I want to construct B1, B2, and B3. I can apply the same procedure. So here I call this the matrix A. So I have to take A inverse and then the transpose. I get B1. That's one method. That's the method I just displayed for the n-dimensional case that will apply here also. Right? But there's another method. So let's say I'm given A1, A2, and A3. Let's look at B1. Because the set of vectors B are reciprocal to A, right? So I'm going to calculate B1, let's say. I'm given this. Right? Given. So B1 I know is orthogonal to A2 and A3. Right? So B1 dotted with A2 is equal to 0. B1 dotted with A3 is equal to 0. Right? Clearly then, B1 dotted with alpha A1 plus beta A3, I'm sorry, A2 is equal to 0. Right? That's clear from this. Take alpha A2, right? Take the dot product, it will be 0. What is alpha A2 plus beta A3, the set of vectors, represent? It's the plane of the vectors formed by A2 and A3. Right? The arbitrary values of alpha and beta will expect to get a whole set of vectors. They will all be on a plane on which A2 and A3 lie. We have already seen that. Right? So now, what this means is that B1 is orthogonal to the plane formed by the vectors A2 and A3. Now we have seen another vector earlier, whose direction is normal to the plane of A2 and A3. Right? So we have seen another vector earlier which is normal to the plane of A2 and A3. The cross product. So since A2 cross A3 also gives a vector in the direction normal to the plane of A2 and A3, I can conclude that B1 is proportional to A2 cross A3. Right? So I can write B B1 is equal to, let's say, some alpha 1, some constant. So we have used two properties of the reciprocal basis with respect to B1, and I've got this far. Now how do I calculate alpha 1? Dot product with which vector? With A1. That's the only one left, right? If I take now the dot product of B1 with A1, that is 1, right? Taking now the dot product, right? A1 dotted with B1 is alpha 1. A1 dotted with A2 plus A3, right? Which would then mean this is 1 because of the reciprocal property of A1 and A on the one hand and the A vectors on the one hand and the B vectors on the other hand. That is very important not to normalize these vectors. These have to be taken as they are. No need to normalize. If we normalize the reciprocal property, we will be lost. We have the coordinate surface and you have to take the gradient and do it as it is, right? So that is what we get. So clearly alpha 1 is simply 1 over A1 dotted with A2 cross A3. So this now gives another method to construct the vectors B1, B2 and B3 from the vectors A1, A2 and A3. So B1 given A1, A2 and A3 can be written as A2 cross A3, the cross product A1 dotted with, and it can be easily shown and leave it as an exercise. B2 then would be given, right, by A3 cross A1 divided by the same quantity A1 dotted with. You have to understand cross product as a sign, so you have to know which way to construct the cross product. So I am keeping this the same. Here this is a dot product, so it doesn't matter when A1 dotted with the cross product or A2 cross A3 dotted with A1. But here it is very important whether you write A2 cross A3 or A3 cross A2. Right? So then B3 is given by A1 cross A2 by A1 dot A2 cross A3. Conversely, if you have B1, B2 and B3 given to you, then A1, A2 and A3 can also be considered using very similar formulas. And again, leave it as an exercise for you to prove. Same set of arguments which apply. All you have to do is to replace A and B. Just interchange A and B, you should get the answer. And so on. I leave it for you to prove it. The same argument, making you take any vector. Suppose I want A1, right? The property of A1 is that it's orthogonal to B2 and B3, so it must be proportional to B2 cross B3. Proportionality constant can be found by simply taking the dot product of A1 with B1. You will get all of these results one after another.
Proportional constant can be equal for all cases.
That's how it comes out to. Because here, and it's just convenient the way you write it, right? Because the triple scalar product is what it represents. What is the triple scalar product? Triple scalar product is A1, A2, A3, the determinant, right? Sorry, it's A1, 1. Be careful because now I have a subscripts on the vectors as well, right? It will be A1, 1, A1, 2, A1, 3. This is the component of the vector A1, right? A2, 1, A2, 4. And you are right. When you follow the procedure, you get probably something else. This might not come directly. However, by suitably interchange, because if I do one interchange, right, then I get A2 dot A1 plus A3, but that will be the negative of what I had, because we know that when you interchange two rows of a determinant, you get the negative of what it was. right? So you can get all the results corresponding to the triple scalar product, right? So I agree that you might not get directly this, but you can always bring it to this, right? So there are all these relations associated with the triple scalar product. So by for interchange these two, what I am getting is actually A2 dotted with A1 plus A3. Clearly, that would be negative. That is indicated by the fact that negative of the earlier one, A1 dotted with A2 plus A3. They are all magnitudes are the same, the signs would be different. So by suitably manipulating the order, you get this in a convenient form. So that for all of them, the denominator you don't have to keep changing. The convenience of writing the formula, you write it in any different way you want, right? So it's very easy to know that the denominator for both the cases you get the same quantity. Now for 1, I have 2 cross 3. It's easy to remember. For 2, I have 3 cross 1. It goes in the cyclic manner. That's how the formula come out. Right? So if you're confused, you go and try to prove this. Right? So this is what we have. Now, what is important to know is that if, for instance, the set A1, A2, A3, SA is orthogonal set, let us say that because the results I have given, do not assume that A1, A2 and A3 among themselves are either orthogonal or orthonormal. Suppose A1, A2 and A3 form an orthogonal set, right? Then what? Then A1 dot A2. So what can you say about B1? Right? Okay. So now we have A1, A2 and A3 are orthogonal. Then A1 dot A2 is equal to 0. A1 dot A3 is equal to 0. Right? So A1 is also proportional to A2 cross A3. We have just seen that B1 is also proportional to A2 cross A3. Right? A1 and B1 themselves are proportional to each other. Right? And it's possible to show in which case that B1 would simply be equal to A1, so B1 is equal to, let's say, some beta 1 times A1, right? Now B1 dot A1 is 1 because the reciprocity still holds, so which means that 1 is equal to beta 1 times A1 dotted with A1. Beta 1 is 1 over A1 dotted with A1. So B1 is given by A1 dotted with A1. And then B2 would be given by A2 by A2 dotted with A2 and so on. You can see that B1 is proportional to A1, B2 is proportional to A2 and B3 is proportional to A3. In the further special case, that this is the orthonormal, then clearly A1 dotted with A1 is 1 and so B1 equal to A1, B2 equal to A2 and B3 equal to A3 and we recover the result, well-known result of this special case, right? That an orthonormal basis set is self-reciprocal. So I've written the formula first. For arbitrary case like A1, A2 and A3 need not be orthogonal, right? Or orthonormal or even orthogonal. When you get to the case where A1, A2 and A3 are orthogonal, then we see that B1, B2 and B3 are effectively proportional to A1, A2 and A3 respectively. The proportionality constant is simply given by the length of the vectors A1 and so on, right? But in the further special case where one of them, in fact the same argument can be made for B1, B2 and B3 being orthogonal, then obviously A1, A2 and A3 would also be orthogonal and it will be simply be proportional to B1, B2 and B3. And if it is orthonormal, I don't even have to worry about the other set, it will just be equal. Right? This sort of completes the cycle. Now we'll see how to apply these ideas to a particular case, a very well-known case that we will discuss at length, the cylindrical coordinate system. From the point, right, and then I connect it to the origin, right. Clearly, the projection of this, I can be able to draw it very perfectly. So clearly, this would be x2 and this would be x1. Because x3 is just a direct projection there. So that's how we construct. When we mean by components, you can simply draw the projection of the point onto the x1, x2 and x3 planes. X3 axis, sorry. So now I have this. The cylindrical coordinate is defined by this angle phi and this distance, which I am going to call as RC. I'll explain the notation. There is a lot of confusion about the notation. This notation is somewhat unusual. If I call this, so the U1 is RC, U2 is phi, U3 simply is Z. There is no transformation of the answer. ZC. ZC is simply equal to x3. Right? So let's now write what they are in terms of, first I can easily write x1 would simply be RC times cosine of phi. Now that I have defined this, RC is the distance from the origin of this projection. That is what I am calling RC. That is one of the coordinates of the cylindrical coordinate system. The other one is the angle it makes with the x1 axis, the O1 axis, that is phi, the angle. The third coordinate is simply the original x3. So I am going to call this as set C. x2 is equal to RC sin phi and x3 is equal to the ZC. Other notations are, this is often referred to as x in the Cartesian coordinate system. This is y and this is z. Now when you come to the notation for the cylindrical coordinate, common notation is to replace RC simply by R and phi by simply theta. This is what Lightfoot uses. So this is fine as it is. The other common coordinate system, if you look at Lightfoot, right? Lightfoot, this would be theta, this would be R, the cylindrical coordinate system. Lightfoot also uses the spherical polar coordinate system. So for the spherical polar coordinate system, right, the spherical polar coordinate system will have this as R. That's the distance from the origin to the point itself becomes R. Right? And then this is the Z axis or the X3 axis. The angle made by this with the Z axis becomes theta. Now it seems really, somewhat odd that two quantities, right, are denoted by the same symbol, but they represent totally different quantities. Right? So this to me is a big source of confusion. And of course, birds would like to strike a cautionary note, and they say that whenever there is confusion, you just may put a bar on the r and the theta and the cylindrical coordinate. Right? Now, as far as the angle is concerned, I see no reason to call this as theta, and it's the same angle that would be called as phi in the spherical polar coordinate. Right? So for me, doesn't look proper to call something that is phi. That phi in the spherical polar coordinate is this angle. So it seems natural to call this also as phi. So there is only one angle in the cylindrical. So why call it theta? But it's actually represented by this angle in the spherical polar coordinate. Now, as far as the other coordinate is concerned, we cannot call it r because that r is used up in spherical. Now, Aris uses rho for this, and I was using it for a time when I taught this, when I realized the moment I go to write the continuity equation, there is already a rho, which is the density of the fluid. Right? There is a problem there also. Rho, but Aris is very correct in my opinion, keeping this as phi, because I think that certainly there can be no argument about it. Right? It has to be phi, and there is no problem at all in calling this phi. There is only one angle, and this remains the same phi when you go to the spherical polar coordinate, where now I have another angle which I will call as theta. Right? So either you call, once you call this theta, you should also call this theta and call this phi, but that I have not seen anywhere. Right? So this one I have seen at least one other book, Bachelor in fluid mechanics, fluid dynamics by Bachelor, uses the symbol sigma for this. That also is possible, but I have not going to use that because sigma is often used as a notation for the stress tensor itself in some books, and probably used for surface tension, which of course we won't use it in this course, but I prefer calling this simply as RC, which is the R in the cylindrical coordinate system. But the spherical coordinate has only one distance r, that is to be distinguished from the RC. So clearly that then leads to this, and we can call this phi so that there is no need to make any change once you go to the spherical polar coordinate. This is simply a notation. But the flip side of this is that if you are using the expressions given for the various operations in Stewart, Lightfoot, he would be using the cylindrical coordinate r and theta, whereas all of our expressions would have rc and phi. So if you want to read out formulae from a standard textbook, you would probably find only r and theta rather than rc and phi. So that's the disadvantage. So we stick to this, right? So now the question is that we've got one of the rays, so we've got x expressed as a function of u1, u2 and u3, x1, x2 and x3. That will directly help me to construct the tangent vector, right? So clearly a1 would simply be dxk by du1. u1 for me is rc, right, times ek. Right? So a1 for the cylindrical coordinate system, dx1 by drc, which will be cos phi, right, times e1. So as I have said, since the curvilinear coordinates are expressed in terms of the Cartesian coordinates, what we are looking for is actually expressing the unit vectors or the basis vectors in the curvilinear coordinate system in terms of the Cartesian coordinate unit vector. So you cannot disregard them. It's not something that is independent of the Cartesian coordinate system, right? So given chosen Cartesian coordinate system, you can ask what are the basis vectors of the curvilinear coordinate system. You have two sets of basis vectors in general. The one which are tangents to the coordinate lines and one which are the ones which are normal, right? So now this with respect to RC, right? So one line. This is the RC line. This is U1. This is U2. This is U3. Cos phi E1 plus sin phi E2 plus what? Plus 0. There is no RC in the third expression, right? So this is A1, A2, exk by U2, EK. Now we have to differentiate with respect to phi, keeping all the other variables fixed. So first I differentiate x1 with respect to phi, right? So that would be minus RC sin phi E1 plus RC cos phi E2 plus 0. A3 clearly is simply equal to dxk by du3, right? Ek, that is simply equal to E3. Right? So, because there is no ZC in either of this, and this is simply differentiating ZC with respect to itself, which is 1, that will contribute to the vector A3, which is nothing but equal. It's not surprising because that coordinate is not transformed at all. So it's not surprising that the basis vector corresponding to that coordinate remains the same as in the Cartesian coordinate system. So now, right? So now what can you say about is the system of vectors orthogonal? It is orthogonal. First of all, A1 dot A3, as well as A2 dot A3 is seen. You have to check everything, right? A1 dot A3, because this has no E3. This also has no E3. So clearly A1 dot A3 and A2 dot A3 is 0. That's clear, right? What about A1 dot with A2? That is also 0 because it will be minus RC sin phi cos phi plus RC cos phi sin phi. That is also 0. So clearly, the basis vectors for the cylindrical coordinate system forms an orthogonal set. So it's only, even though it's a curvilinear transformation, it is an orthogonal transformation, right? Because the point though is that in contrast to mere rotation of the Cartesian coordinate system, this is different because you can say this will be the defining property of the curvilinear coordinate system that will make most of the manipulations more complicated than with the Cartesian is that the unit vectors themselves are dependent on the coordinate, whereas they are not in the case of the Cartesian. The Cartesian, wherever you go, it's the same unit vectors E1, E2 and E3. Here, depending on the phi and RC, those are the variables that determine, the unit vectors themselves are changing the position. So at each point, you have to look at a different set of basis vectors. The formula is given by this, right? So clearly this is an orthogonal set. So all practical purposes, it's an orthonormal set except for this is orthonormal unit normal because cos squared phi plus sin squared phi. This is also unit norm. This is not, because this is norm of this is the RC, which may not be equal to 1, right? So only one of the vectors is not a unit norm. Now, to construct B1, B2 and B3, I can make use of this formula. So one way would be to construct, I will leave that as an exercise for you to do. It's a good exercise, is that to construct B1, B2 and B3 directly from the normal to the coordinate surfaces. For that, I need to express RC phi and ZC in terms of x1, x2 and x3, right? So that, if you wish, we can do it in the next class, but for that, RC is given by x1 squared over half now I have taken normal, right? So that would be taking this. So this is the function, this is the variable u1, so this is the function u1 expressed as a function of x1, x2, x3 is not there. Here also x3 is not there, here x1 and x2 are not there. We have to take a gradient vector directly, right? I leave that as an x6, but here, since the formula I have already defined here, obtained here for the orthogonal system, but I now write b1 will simply be proportional. So b1 actually will be equal to a1 because a1 has unit norm. So I can immediately write those formulas. b2 will not be equal, b3 is equal to a3. Right? Because the formula is b1 equal to a1 divided with a1 dotted with a1. Now here, two of the unit vectors have unit norm. So for those vectors, b1 and a1 as well as b3 and a3 would be the same. Right? But however, b2 is equal to a2 divided by a2 dotted with a2. Right? So that would be right, minus rc sin phi ex plus rc cos phi e1 divided by a2 dotted with a2 would be rc square sin square phi to rc square cos square phi, that would be rc square, that would be divided by rc square, and that simply would be minus sin phi ex plus cos phi e1 divided by rc, rather than multiplied by rc. That would be b1 b2 b2. But for all practical purposes, even this is actually proportional to that. So when we are now going to form the basis vectors, because we know that once you have an orthogonal set, right, it's very easy to construct an orthonormal set by simply making all of them unit norm. Okay, two of the vectors are already unit norm. So I will now combine all of these results together, right, to construct. This is A1. Let's fill it out. We can construct the unit norm basis vectors for the cylindrical. There is no need for the reciprocal basis here effectively, because I effectively have an orthonormal set. Right? So I don't need to consider the two sets of vectors at all. They are all proportional to each other. So I now define ERC as the first vector. That will be given by cos phi E1 plus sin phi E2. So it's very important to remember this picture also, right? So that how it is being transformed, you can see. Because in actual problems we will be using x, y, and z. So we define the x, y, and z axis suitably. Right? So P phi would be the unit norm of this would simply be this divided by the norm, which is simply RC actually. Right? So that would be minus sin phi E1 plus third vector, which I will call as EZC, is simply equal to E3. So these are give the expression of the basis vector. This is an orthonormal basis set now for the cylindrical coordinates. This is what we'll be using from now on. Right? So because they are orthonormal, we make many of the calculations much simpler than if they were not orthonormal. Then we will have to bring in the reciprocal basis vectors. Right? It's also useful to express inversely even in terms of ERC, E5 and EZC. The inversion of this. So how would you do that? You can of course invert it, we consider this as a matrix and simply invert it. Another way to do it, of course, another way to construct B is construct the matrix of A1, A2 and A3, right? So that would be, let's construct the matrix A. That would be A1 vector would come in, so that would be cos phi, sin phi, 0. Right? Because I recognize it's these are all different ways. It would be good exercise for you to try them out. Right? One is, as I said, to take the gradient of these functions. Right? Another is what I have used. The fact that they are orthogonal, I have made use of to use the formula for that case. A third method would be to take the inverse of the A matrix and then the transpose. Right? So for that I will construct the A matrix minus in the A matrix, we have to take an inverse and then take the transpose, and the columns of that matrix will give me B1, B2 and B3, which of course I have already obtained to us easier method. Even E2 and E3, because of the fact that ERC, E5 and EZC are orthonormal, even can be easily written as ERC plus E1 dotted with E5, E5 plus E1 dotted with EZC, EZC, right? E1 dotted with ERC simply ERC dotted with E1, right? That I can easily cos phi ERC plus E1 dotted with E5 would be minus sin phi E5, and E1 dotted EZC is of course 0. So this is what I will get. And E2 is simply E2 dotted with ERC, which will be sin phi ERC, right? Plus E2 dotted with E5 would be plus cos phi E5 plus 0, and this E3 would simply be EZC. Those are correct, right? So these are the inverse relation. They will be useful at least in one of the operations that we would do. So now the basic vector operation, for example, if you want to take the dot product of two vectors or even the cross product of two vectors, because of the orthonormality property of the cylindrical coordinate basis set, it will give rise to the same formula. Right? Basically what we want now, the any vector A, earlier I was expressing them as, this is now an arbitrary vector. You should not confuse the A1 I have here, right? What would be, let's take the velocity. Now what we will now express is in terms of BRC, ERC plus B5, E5 plus EZC, EZC. This is how we are expressing, right? And we want to take the dot product of this, need not be the velocity, let's say some other vector U, when it's also given in the cylindrical coordinate system. Clearly, because of the orthonormality property of the cylindrical coordinate basis vector, B dot U is simply equal to BRC, 2RC plus B5, U5 plus that's what we would get. And so some of these operations would be very similar to what we had for the Cartesian coordinate system. But the most important difference will come when you look at all operations involving the gradient operator. You will be starting from the gradient of a scalar to the divergence of a vector, to the divergence of a tensor, to the gradient of a vector. All of them, the complication that would come in is the fact that, for instance, if I want to take the gradient of a scalar, that's one issue, let's say I want to take the divergence get the formula for the gradient operator, but the main problem will come because of the fact that the unit vectors themselves are dependent on the coordinates, and we expect the gradient operator, right, will involve the derivatives in the cylindrical coordinate system, derivatives involving d by drc, d by d phi, and d by dzc, right? So when I'm operating it on something, it is a vector, right? When the vector is represented by this, let's say, now not only drc, d phi, and dzc are functions of rc, phi, they are not a function of z, but at least erc and e phi, right, are dependent on phi actually. There's no dependence on rc also in this case, but they are both dependent on phi, right? So that would make the operations a bit more complicated because the unit vectors themselves are dependent here of course on one of the coordinates, but in a general curvilinear coordinate system they could be dependent on all three curvilinear coordinates. So we need to consider not only the derivative with respect to the components, but also the derivative of the unit vectors themselves with respect to the coordinates, right? That we will see how that complicates the matter in the next class on. What I will do in the next class is also define the spherical polar coordinate system, because we don't have, we can't have time to do everything for all the coordinate systems. So as I explain how to construct, let's say, the gradient of the scalar or the divergence of the vector or the divergence of the tensor to the cylindrical, you should go back and do the same thing for the spherical polar, so that it's a good practice for you. So don't expect me to give it as a separate assignment. As and when we do an operation for the cylindrical coordinate system, you should go back and do it for the spherical, where there will be more complication, right? Because here only the phi, the only variable that appears in the basis vector, there will be an additional variable theta that would appear, that would make the operation more difficult.